Alright, so in this video we're going to go over what's called the Nth Roots Theorem and then see an example of how to use it. So the Nth Roots Theorem says, hey, if we have a complex number written in trig form, RCIS theta is a complex number as long as we're dealing with a root that's 2 or bigger. So n is a positive integer, 2, 3, 4. So square roots, cube roots, and so on. Then as long as the original root isn't 0, so if the complex number was 0, then this doesn't apply. But as long as it's not, then it turns out there are actually, if n is the root we're taking, then there are indistinct roots, nth roots of w. And the way that we find them is we take the magnitude of w, do the nth root of that, and then it's CIS, take the angle, divide it by n. Okay, that would be your first solution for zk, because what we're looking for is when I raise this root to the nth power, I should get w back. So of course, if it was theta over n, if you multiplied theta over n by n, because it's the nth power from de Moivre's theorem, then you get back to theta. What the plus 360k over n is doing is it's looking at all the other solutions that are coterminal. But when we divide them by n, they would all still be within the original intervals 0 to 360 or 0 to 2 pi. And so it turns out as long as k goes from 0 up to n minus 1, these are all going to be distinct because the angle will be an angle between 0 and 360. Or if we did it as 2 pi k, then in radians, it'd be between 0 to 2 pi. So another way of just simplifying this formula, which is the one we often use, will be nth root of r, and then theta over n plus 360 over n times k, just distributing the n through. So with that in mind, let's consider an example here. We want to find the 3 cube roots of 8. Of course, everybody knows already that one of the things that if you cube it, you get 8 is 2. 2 is a cube root of 8. But it turns out there's 2 other ones that you're usually not aware of. 2 other things that if you raise them to the third power, we would get 8. So first thing we do is take that number 8, and we have to write it in trig form. So of course it's 8 plus 0i. So it's on the x-axis. It has a magnitude of 8. And the angle, of course, is 0 degrees or 0 radians. So we can rewrite 8 as 8 CIS 0 degrees. Then we want to apply our formula for taking the roots. We want cube roots. So zk would be the cube root of 8 CIS times the 0 degrees divided by 3 plus 360 over 3 times k, where we're going to be letting k go. In this case, k equals 0, k equals 1, and k equals 2 to get our 3 roots. So we go ahead and simplify. Of course, cube root of 8 is just going to be 2. And 0 degrees divided by 3 is just going to be 0. 360 divided by 3 will be 120. So this is going to be plus 120k. CK is going to be 2 CIS 120k. And so then we just let k be 0, 1, 2, 1, and 2 to get our 3 different roots. So z sub 0 will be 2 CIS 0 degrees. We can expand out. 2 times the cosine of 0 plus I sine of 0. And of course, cosine of 0 is 1. And so sine of 0 is 0, so this doesn't have any imaginary part. So there's the normal cube root of 8 that you're used to thinking about, 2. But we can go and compute z1 and z2. z1 would be 2 CIS 120 degrees. Oops. Sorry there, I got messed up there. So there, we're back. 2 CIS 120 degrees, which is 2 cosine 120 plus I sine of 120. And then, of course, cosine of 120, that's a reference angle of 60 degrees. And so with a reference angle of 60 degrees, cosine is 1/2. But he's in the second quadrant, so it's going to be negative 1/2 times 2 gives us negative 1 for the real part. Sine of 120 would be square root of 3 over 2. So we'll have plus I times square root of 3 times 2, which would just be I squared of 3. So we have 2 times negative 1/2 gives us negative 1. 2 times square root of 3 over 2 gives us square root of 3 to go with the I. So if you took that thing and raised it to the third power, you will get 8. And you can see it really easily in trig form. 2 to the third is 8. 120 times 3 is 360, just the same as 0. So it would be 8 CIS 0, which of course is just 8. So you can see it really easily in its polar form that if you cube it, you are going to get back to 8. But if you took this thing and algebraically multiplied it times itself 3 times, it will also be 8. And then Z2, we just let K be 2, so it'll be messing up again, sorry. 2 CIS, 240, and then again we write it out. 2 cosine 240 plus I sine of 240. 240 is in the third quadrant with a reference angle of 60. So cosine is going to be negative 1/2. And sine is going to be negative square root of 3 over 2. So we get, of course, negative 1 minus I squared of 3. And again, if we took this thing and plugged it into the Maury's theorem for the third power, 2 to the third would be 8. 240 times 3 would be 720, which is the same as 0 degrees. So we're back again to 8 CIS 0, which is just 8. And if you went to the next one, if you went and tried to put 3 in for K, you're actually going to be back to 0. Because for K equals 3, that would be 2 CIS 360. Which 360 is the same as 0. That's why we only go up to 1 less than the number. So we go 0, 1, 2, and then that's it. Now, the last thing I want to show you here is how these roots kind of go together. So what I've done here is taken and graphed the 3 points 2, 0 for 2 plus 0i, negative 1 square root of 3 for negative 1 plus square root of 3i, and negative 1 negative square root of 3. And you can see that these roots, these cube roots of 8, are equally distributed about this circle of radius 2, because cube root of 8 is 2, its magnitude is 2. So they're equally distributed. And of course, being cube roots, take the circle, divide it up into 3 equal parts, you get 120 degrees each. So they're all equally spaced. Once you have the one, then it's easy to find the others because they're always 120 degrees apart. Okay, and that's actually something you're going to find is pretty common with all of these root problems. If it's square roots, they're going to be 180 degrees apart. If it's fourth roots, they're going to be 90 degrees apart. Fifth roots would be 72 degrees apart. Just taking the 360 and dividing it by whatever root we're taking.